motors, right? Yes. So DC shunt motor, speed control of DC shunt motors. There are three methods coming under speed control of DC shunt motors. So first method is flux control method. Okay. So before going to what is given in this circuit diagram, I will tell you how it is controlled. Okay. So you have to first recollect what is your EMF equation. EMF equation of DC shunt motor is proportional to your flux and your speed, right? Right, guys? Do you yes, yes, I suppose you can recollect this formula or recollect the concept how the EMF was actually derived, right? Flux into your speed. So now here that you are controlling your speed, okay, your EMF is fixed. Your EMF is fixed, right? You are giving a standard supply here without any variation of your voltage. So your EMF is fixed. So how can you vary your speed? You can vary by varying your flux. So what is flux? What is flux? Flux is actually the product of your field poles, right? So field poles, how can you control your flux? By varying the field current, IF. When you vary your field current, you can what? You can vary your flux. So flux will control your speed. When you increase your flux, your speed will decrease. So this is how this is working. So when I vary this resistance value, my current in my field winding will what? Will vary. If I increase this resistance, the current flowing through this winding will decrease. So obviously my flux will decrease and speed will increase, right? So this is how this flux control method is used. And now coming to the armature voltage control. So in armature voltage control, they have achieved the speed control based on what? Based on varying your EMF. Here your flux is fixed, you are varying your EMF. How am I varying my EMF? Because my EMF is V minus IARA, right? So here if I vary my resistance value, by varying my resistance value, what will happen? What will happen? So by varying my resistance, the voltage drop here is increased. So my EMF value will also decrease. So obviously my speed will what? My speed will decrease. Okay, this is how the speed is reduced. So you can reduce your speed by varying your, increasing your armature resistance, decreasing your current, sorry, increasing your armature current resistance will decrease your current, your voltage drop will decrease and EMF will increase and your speed will increase. Okay, when you increase your resistance, what will happen? Your drop will increase here, sorry, your current will decrease and your, when by increasing your resistance, sorry, I think I'm confusing you guys, I'll explain it again. So your EMF is V minus IARA, right? So by increasing your resistance value, your current value will come down. Okay, overall value will decrease. Okay, so when your current decreases, by increasing your resistance, your voltage drop will decrease. Okay, so what you are affecting your EMF, right? When your drop is decreasing, your EMF value will increase, right? So what will happen? Your speed will improve. So this is how when you decrease the value of resistance, your current flow will increase, and your voltage drop will decrease, and your speed will what? Decrease. So this is how you can achieve the speed control by varying your armature voltage value. Okay, so now coming to the Ward-Leonard method. Here the advantage of Ward-Leonard method over your other two methods is you can achieve the smooth control, which is not possible here. Your resistance value will be varied only step by step. This is somewhat similar to your step control, but you won't achieve your smooth control. But while moving to the Ward-Leonard method, it is possible to achieve the smooth control. So let's see what's happening in your Ward-Leonard method. In this method, you are connecting your DC shunt machine to a generator. Okay, and this generator is a separately excited generator. This is a separately excited generator where you can vary your field. Okay, you can vary your field here, and this is a motor which can be AC or DC. Okay, this motor is giving the mechanical input to your generator. Okay, so you can also vary your terminal voltage here, so you can achieve both 1 and 2. So you can vary your field here, and you can vary your terminal voltage here. So by applying both these methods and by having a smooth control over the applied voltage of your DC shunt machine, you are like achieving the smooth control, and you can vary both your flux and your resistance. So you can operate it in very wide range of speed. Control is possible. So when compared to the armature voltage control or armature resistance control or flux control method, Ward-Leonard method have advantages. Like when we talk about advantages of number 3, number 1 is smooth control is possible. Why? You are not dependent on resistance or rheostats. You are directly controlling your voltage. Okay, so number 2, wide range of speed control is possible. Okay, you can vary your speed to very high value or very low value. Okay, so because you have control over your flux, when you have control over your flux, you can increase the speed. You can go very high speeds. When you have control over your terminal voltage, you can decrease your speeds. You can go to very low values. So this is applicable for low speeds, and this is applicable for high speeds. Because when you have control over your flux, you can only decrease your flux, okay, by increasing the resistance value. So you can achieve higher speeds here. But here, when you have control over your terminal voltage, you can reduce your speed, okay, by decreasing your EMF value, by increasing your resistance. You can decrease your EMF value here, okay, by increasing the drop here. You can decrease. When you go for Ward-Leonard method, it is possible for wide range of control. This is about speed control of DC shunt motors.